Imagine you are searching for Waldo. Finding him in a page full of people, objects, and colors is difficult until someone says, "Look for red and white stripes." Now, you stop scanning everything and focus your attention. Well, deep learning models work in a similar way. A neural network sees millions of pixels when searching for a tumor. They develop generic filters, focusing on finding basic edges and textures that help them find what they are looking for. But in medical imaging, we're trying to do more. Our work is about designing and discovering field-specific filters that guide the model towards finding the tumor-like patterns. Our approach to explainability is not just asking, "What did the model see?" We're also actively telling it, "Look here, this is what matters."
To decode the black box of medical AI, we're not just watching the model, we audit its internal logic. Previous research showed that models naturally learn handcrafted LTEM, like L5E5, which detects edges. But we want to go further. We set out to identify the unique patterns that the models developed on their own that might be more effective for mammography segmentation than standard filters. Our audit uses two tracks. First, kernel ranking uses an ensemble of statistical techniques to identify which internal filters hold the most diagnostic information. Second, Fourier transform approach allows us to extract feature maps and apply an inverse Fourier transform to calculate the learned optimized kernels. By studying these discovered kernels, we identify specific textural patterns that can be associated with margin sharpness and shape. This discovery phase is then used to inform the rest of our pipeline architecture.
Our architecture is designed to bridge the gap between deep learning accuracy and clinical trust. Here is how we turn a simple image into a validated medical report. It starts with FCBFormer. We process the input region of interest through two parallel branches, transformer branch for global context and a fully convolutional branch that acts as a local texture expert. These streams fuse to create a high precision segmentation mask, isolating the lesion with 85% accuracy. Next, we feed this masked region into a multitask Swin transformer. Unlike standard models that give a single label, our hierarchical network splits into three distinct prediction heads, simultaneously determining pathology, shape, and the final bias category. But a score isn't enough. We extract the feature maps from our expert branch and apply a specific loss kernel L5E5. This acts as a mathematical lens highlighting high-frequency edges to calculate the texture energy measure. This allows the system to explicitly see and verbalize features like speculated margins. Finally, we bring it all together. The data aggregator combines the deep learning predictions with the visual texture evidence. This synthesis generates a comprehensive medical report, providing clinicians with not just a diagnosis, but the visual proof to validate it.
From the Fourier transform approach, a kernel highlighting diagonal patterns was obtained, which can be observed in the convolved mask. From the kernel ranking approach, a kernel with a vertical orientation was obtained that detects sudden intensity changes along the vertical axis. The accuracy results show an IOU of nearly 0.85 for both approaches, and the segmentation results can be seen below. The Laplacian pyramid visualization of one kernel fused with the original image also reveals diagonal textures across each scale. Our work goes a step further from traditional filters by identifying kernels that respond to mammography-specific textures. This shifts explainability from generic filters to domain-specific visual evidence, making the system interpretable and more responsible.
But we know that in medicine, accuracy without explanation is just a guess. Our next step is clinical validation. We will test our generated reports with actual clinicians to measure the human impact. Our goal is to prove that an explainable AI companion doesn't just verify a diagnosis, it saves the radiologist valuable time. Whoa, here is Waldo.